Thanks, Jasmine, and welcome everyone to this second webinar of BIPVBOOST project. We had a previous webinar on digitalization, which is already live in the WIP YouTube page, if I'm not wrong. So I invite you to check. And today we are focusing on standardization, innovations and results from BIPVBOOST project. So my name is Jose Mari Vega de Sebane. I'm the project coordinator from Tecnalia, and I'm pleased to be here on behalf of the consortium presenting the results we achieved during the project on this topic. So we will start with a short presentation from my side on the overall results we achieved during the project, an overall overview of the project. We will then move to Fabio Parolini from Subsea, which will present the developments on the standardization topic on mechanical and electrical safety. Then we will move to Simon Baudard from CSTB, which will talk about fire reaction. And we will close with Daniel Valencia from Tecnalia on energy economy topic. We will leave questions to the end, so please note them, and we will have time to discuss at the end of the session. This webinar will be recorded and it will be also uploaded in WIP's webpage, YouTube channel. Sorry. So I will share my screen. 1 second. Okay. Jasmine, can you confirm if you can see the screen?
Yes.
Yeah.
Perfect.
It's okay. So, yeah, BIPVBOOST project is or stands for bringing down costs of multifunctional building integrated photovoltaic solutions and processes along the value chain, enabling widespread near zero energy building implementation. It is H2020 project coordinated by Tecnalia on the topic demonstrates significant cost reduction for building integrated photovoltaic solutions. It started in October 2018 and will end in May 2023. So we only have a few days left. We will then move to the reporting. It is a consortium project with 19 partners from 7 countries, which cover the most relevant part of the BIPV value chain. We have from equipment manufacturer to BIPV module and system developers. We have end users and a series of other relevant stakeholders in the value chain. Very briefly, BIPVBOOST at a glance. So we intend to move from iconic BIPV, and we're trying to achieve the mass implementation of this technology in all segments, including residential, industrial, and commercial segments. We have nothing against iconic BIPV, but we really need to move to a next level in the implementation of this technology in the construction sector. For that, the objective of the project is to reduce the extra cost associated to the PV part by 50%, as set by the set plan for PV. And we intended to do that by implementing a holistic roadmap of activities that bring cost reductions in different levels of pillars, starting with advanced manufacturing, also including BIPV envelope solutions, optimization of the cost reduction, and also reliability topics related to BIPV modules and systems. To progress in the digitalization tools along the value chain, supporting design, installation, and also manufacturing, and then also tackling BIPV specific standardization activities, which is the topic of today's webinar. I will present now briefly the main results we achieved in the project in all these pillars. Starting with a flexible manufacturing line for BIPV, we developed a flexible taper stringer for crystalline silicon technology, which allows an automatic string layup compatible with big formats up to 3 by 2 meters, which allows an accurate free positioning of strings onto the module. Also allowing an in-quality control at string and module level prior to the lamination process, reducing rejections and delivering cost reductions associated to the manufacturing. We can manufacture in 2 modes, standard, so high throughput, or customized, so lower throughput but higher flexibility. And we can be compatible with full, half cells, bifacial cells, and customized strings, including different lengths and also cell distances, including variable cell distances within the same string. So overall, we achieved a flexible equipment which allows a higher productivity and quality and a reduced module production cost. The equipment was developed by Mondragon and is now being demonstrated at Onyx facilities in Avila. Then we have the portfolio of low-cost and aspherical BIPV solutions. We have developed a set of new BIPV solutions, including a set of glass BIPV products based on crystalline silicon, back contact, and amorphous-silicon technologies from Onyx Solar. We have developed a multifunctional battery kit with integrated insulation by PITS, and also the collaboration between Flisson and Schweitzer for the development of a BIPV roof and facade system based on a CIGS or metal technology. And we have also a low-cost click-and-go substructure for easy and fast installation of BIPV modules by Tulips. These solutions were developed and demonstrated in the frame of the project, as we will see later on. We have then a set of digitalization strategies covering different topics in the value chain. We have on the first hand a BIM-based collaborative platform for data-driven cost reduction on the BIPV process. This is basically based on Enerbeam's software called BIM Solar. We have also 3D with a cloud-based energy management system for tertiary buildings, which include the BIPV generation, storage, and manageable loads, and also the development of a BIPV digital twin and a failure detection and diagnosis tool for BIPV. There was a webinar covering this topic last week, and as I said, this is available in the YouTube channel of WIP. And to finish, we have the standardization activity, which is the topic of today's webinar. We had a long and fruitful discussion during the project on how should BIPV testing look like in order to cover both photovoltaics and construction requirements simultaneously. And we managed to progress in different topics, including energy efficiency, energy performance in non-conventional scenarios, mechanical performance of BIPV, and also fire reaction. We are now in direct contact with ongoing standardization activities, and there's of course public material available in the web page of the project. And to finish, I will provide an overview of the demo sites we built during the project. We have the first demo site in Nisfog, Puerto Llano in Spain, which includes bifacial balustrade manufactured by Onyx Solar, and also a walkable floor using back contact technology, also manufactured by Onyx Solar. We have a second demo site in Mondragon Assembly in Arechavaleta in Spain, in Mondragon's headquarters. This demo site allowed to demonstrate the flexibility of the new manufacturing line, and also the click-and-go solution from Tulips. It is based on a glass technology by Onyx Solar, including the click-and-go substructure of Tulips. Another view of the facade. The third demo is at Mons in Belgium. It is the house of one of the partners, Optimal Computing, and we will have a stakeholder event during the last general assembly in the 24th, 25th of May. If you are by the area, don't hesitate to check and well, register for this demo visit. And at last, we have the demo site at PITS in Borvegno in Italy, which includes the Vetture Kit product in the top part of 2 buildings, which also include the standard solution from PITS. A few messages. So we have a public material available on the website covering different interesting topics. We have reports on cost competitiveness status of BIPV in Europe, cost reduction roadmaps, market and stakeholder analysis, and studies covering the potential contribution of BIP systems to NCEP constructions, standardization, BIM. So please go and check. And yes, a final reminder on the series of webinars we are holding. We have this demo visit on the 24th of May, as I mentioned, and we have a last webinar scheduled on the 30th. We modified this a few moments ago, the 30th of May, on the innovation at manufacturing BIPV system level and BIPV cost competitiveness in Europe. So please save the dates. And a last communication, we have also an upcoming project that started recently in January, which will continue somehow producing contents on not only BIPV, but integrated PV in general. So the project is called Seamless PV. It is also coordinated by Technalia, and the website is already live, so you can go and check. Although we are starting, and we still need to work on the project to create the contents. But stay tuned, and let's move to the speakers now. Thanks a lot.
Thank you, Jose Maria. Now we would like to give the floor to Fabio.
I can share my screen.
Yes, thank you.
Can you see it properly?
Yes, thank you.
Okay, good morning, everyone. I'm Fabio Paronini, subsea researcher in the Innovative Envelope team of the LUIS Competence Center for BIPV. Let's start the presentation right away. Today, we will discuss BIPV through new solar architecture, the missing gaps, and the regulatory environment. We will see a new approach taken and a new testing procedure for BIPV. I want to start right away with 2 joined but contrasting sentences. In the first one of 1999, the problem associated with architecture integrated PV were stated. In the second one, you can find implicitly show how integration in 2018 is perfectly successful. In fact, with the first sentence, there's a problem with the color, with the size, and the limitation of the photovoltaic. In the other sentence, the integration is well successful, and nobody can know the integration of the solar cell in the building. But as a solar energy, one must consider BIPV as a building product that must be customized and able to adapt the shapes, colors, and function. And the product, it must be flexible, is a main requirement from the architect, the flexibility of the product. The BIPV product must be multifunctional and can require transparency as well as opacity. This flexibility linked to increasingly innovative and dynamic technological process has led BIPV to the expression of different architectural languages using solar technology. For example, in the images, you can see colored models, you can see imaging of facade with different shape. And in this context, the Horizon BIPVBOOST 2020 project has taken up some important challenges, including reducing production costs for effective market deployment. And however, today in this presentation, we will focus on product quality assessment. As the title shows, what is needed to transfer BIPV products to the market? It's important to understand that these multifunctional products contain building characteristics and electrical ones. The product must be of quality by meeting the standard. But provocatively, what are the standards that we need and that we can use? The PV part added to the building part does not make the BIPV module. Currently, there is still a lack of clear regulatory framework for BIPV product. There are in gray in this gray area. Sometimes the product were considered as PV standards, and other times the BIPV are considered as a construction product. And in this slide, you can see how for a BIPV product, you have to consider the structure of the European legislation. In order to achieve the imposed goals, you qualify products through compliance with directives and regulation. For building product, and BIPV is a building product, the electrical part is fundamental because they made by a PV part inside. And the K directive is the low voltage directive, which refers to ESC 61730, our harmonized standard for this product. And the construction products regulation, named the CPR in Europe, is the main reference for the building part. Through the EAD, European assessment documents, which are harmonized technical specification developed by IOTA as the basis for the European technical assessment. This construction product is validated through the European assessment document. But which one should be followed for BIPV? The low voltage directive or the CPR? There is still clarity to be gained in this scenario, and the BIPVBOOST project has tried to clarify this aspect. Through a specific workflow, it was possible to determine the main requirements, avoid redundancy and shortcomings, and by involving stakeholders, we can find the 4 main requirements for BIPV. Here are reported for all 4 requirements, but we will only see the electrical and mechanical safety requirement today. As a project outcome was deliverable 5.1, which highlighted the current missing gaps and it proposed a new approach to qualify BIPV products and paved the way for the new testing procedure, specially developed in this European BIPVBOOST project. The three main topics developed in the new electrical and mechanical procedures concern the thermal behavior in non-conventional scenarios, the electrical safety, durability, and reliability, and the mechanical performance of the BIPV product. Therefore, a procedure was developed to consider the additional heating of BIPV modules due to their nature and the fact that they are subject to frequent and continuous shadow scenarios in real installation conditions. Combining several existing standards with specially developed equipment resulted in classifying products by temperature and correlation between outdoor and indoor method and condition. BIPV modules are subject to the potential degradation and seen during the test execution how their behavior is led to developing the second procedure. The main results obtained with the new aging cycle thermal test protocols, and these tests are reducing the number of the sample used for verify the reliability of the product. And they determine change in insulation resistance during test conditions that recall reality. In fact, we can find some samples that during the test have changed their properties. The same was applied to the third procedure, where the possible overheating and limited dissipation can sometimes create problems for protection systems, such as bypass diodes. The procedure development determines, according to the categories found, the behavior of the diodes and the verification of the thermal runway. Now, I show you the procedure inherent the impact of external body. It could be possible to develop this procedure for hard body impact and soft body impact. In fact, the procedure was developed for both of them and applied to the mechanical part. As I seen, the pass-fail criteria reported in IEC differ from those in the European assessment document, where a class of resistance is considered depending on the position and the function of the element. Also, the two parts, electrical and building, do not consider the joint behavior and the safety of the two joint aspects. And finally, the behavior of BIPV modules was evaluated at different temperatures, resulting in different results. In fact, the first test and the results showed the design samples good behavior for both the electrical and building parts on all modules tested in BIPV project. In the picture, you can see a facade product, the EPIT system, for which compliance with the requirements were verified. And in image, you can see the hard body impact made with a steel ball and the larger soft body impact with a higher spherical bag as defined in the European assessment document. The first test and the result showing a good behavior, but it's important to consider the different behavior relating to the temperature of the test, because the temperature of the test could lead a different result. In fact, in this slide, you can see the different behavior at different temperature. I do not enter into detail, but it's important to understand that when we conduct some tests at different temperature, we find out different module damage in the solar cell. For example, in the first image, the test was conducted at standard test condition, and the impact, maybe I change my in order to show you better. This is the impact point in the module, but some factors occurs in the other part of the module. When we conduct the test at the higher temperature, 90 degrees, the methodology of the breakage is completely different. And even in this case, the breakage arises in some other part of the modules. And a different behavior was found at a temperature of minus 25 degrees. The impact point is here, but a completely different breakage occurs in the module. And the procedure can join this behavior on the mechanical part to the electrical one. And we conduct tests in order to guarantee the insulation resistance of the product. Go ahead in the conclusion, and I report here a summary of what I presented today. The quality of the IPV multifunction product is framed between electrotechnical and construction part, and is need a new approach that could combine both PV and construction requirement. And this new approach consider the limit states, the material, the combined temperature of the test in order to find out the best process to qualify the product. And provide a pre-normalist reference to revamp the European standard. It's important to understand that this point allow us to report outcomes, adaptation of existing qualification frameworks to the coordination with ongoing European and national initiatives. For example, the new revision of EN 5583 or ESC 62639. And another outcomes from the European project is participation in the national, European, international working groups. For example, SEAD in Switzerland, Technical Committee 82 in Europe, and International Energy Agency at international level. And a new European project as a follow-up of the BIPVBOOST project, consider this topic and develop furthermore topics regarding not only BIPV, but as Jose Maria mentioned it before, integrated PV model. For me, that's all. I hope to respect the time, and if you have any question, feel free to ask me.
Thank you, Fabio, for your presentation on mechanical and electrical safety. We will save all the questions at the end. So now I would like to give the floor to Simon. He will talk about a fire reaction, fire safety.
All right. Well, do you see my screen?
Yes, perfect.
Okay, I put it in full screen mode. I'm in full screen mode or not?
Yes, you are.
Yeah, okay. Hello, everyone. Thank you, Yasmin. Thank you, Chema. I will present you our contribution in BIPVBOOST project, dealing specifically with fire reactions and how we have developed and improved this fire protocol in order to be most demanding and provide most results to support BIPV dissemination and application of BIPV products in more and more building elements. Well, here is a presentation of the content of my presentation today and how we tackle BIPV system in the current standard environment, and how we handle this situation and this fact to develop more specific standard procedures to provide most truth or most interest for BIPV application for buildings. Currently, when we are talking about BIPV elements, we have to talk about CPR, of course, but also IEC standards. And when we have to deal with the both of these elements, we have to combine CPR building codes elements, and we have a very long list of standards and also IEC requirements. And it's a conjunction of these two roles in order to define which kind of standards we have to follow. And unfortunately, when we are developing a new BIPV elements, we are in front of a lack of standards, and we have to create or to follow some specific standards, not really tuned or fit correctly with our expectations. Well, what we have developed in this work, it's a comparison of standards applications and how we will be able to go through the current situation of standard lacks, or which kind of gap we have to provide to fit and to assess correctly BIPV elements. When we have a look on PV building parts, often it's a very straight pathway with very clear standards to follow, with a very dedicated duration of assessment with IEC, SENELEC, CPR, ATAGs, and we reach the market just after the evaluations. When we have to deal with BIPV elements, it's not really exactly the same pathway. It's a little bit more complex before we have to handle very specific elements due to technical controllers dealing with the integration mode and all elements dealing with building requirements. So we have building categories, BIPV categories also, building parts if we are on a facade, on a roof, and some specific investigation to deal with in order to be compliant with CPR and ATAG, LVD, and so on. Often that drive to additional technical controller requirements with specific changes, new materials to be used, or additional tests. And then after we are able to reach the market. And often it's, as I said before in other presentations, it's like an infinite loops, because we have a lot of incrementations, contribution to provide in order to reach the final accreditation or technical assessment. And when we are comparing the duration of the both, it's quite long to reach BIPV accreditation or assessment, because we have to handle this kind of loops to correctly assess BIPV elements. Well, what we have provided in the IPVBoost project, it's to find a way to support the growth of the IPV market and how we will be able to reduce time and cost of the IPV assessments. To bring more competitiveness, of course, because we want to push a bit the IPV elements for buildings, but also to ensure similar access to market time as PV elements, just to be sure that we are promoting correctly the IPV components. And of course, we want to improve confidence in the IPV solutions, not to change or to shift current standards, but to improve current standards and to be more demanding, just to be sure that we are correctly assessing the IPV elements based on current standards. Our objective is to define a BIPV as a real building element. It's not often the case, and to support, of course, innovations in the IPV field. As already been mentioned by Chema or Fabio, often the IPV elements are on demand or very customized elements, and we don't want to stop the innovations. We want to support it, and we want to develop a specific assessment protocol just to be sure that we are supporting correctly the innovations and to reach correctly the market. Main idea is to reduce the duration of any kind of assessment similarly, and to have exactly the same cost and the same test durations. And we dealt with the cost by combining protocols on the same labs during the same time lapse, just to be sure that we are able to handle correctly these questions and to reach exactly the same guarantees as PV elements. The issues we have been in front of have to deal with 3 different approaches that have been studied in the BIPVBOOST project, with 3 ways to develop a new standards. And we have selected the 3rd options concerning and to dealing with exactly the same time baseline, but also to identify a new pathway to correctly assess the IPV elements. And based on a significant or relevant part of standards, to identify possible combinations, additional or of several relevant standards, and to have a process adapted to each demo case developed or created in the project with a similar methodology validations by partner experts in BIPV. It's a very important idea to have a very specific methodology that could be applied to any kind of typologies of BIPV elements. Well, in order to apply a combination approach on fire tests, because this is the subject of the presentations, we define a new working pathway to develop specific BIPV assessment solutions. Validating the new test procedure by an experimentations, just to be sure it's not just a standard writing, but also validated in the labs. To reproduce the most realistic test conditions at system-wide, not just on samples or very small elements, but at system-wide to give more representativities to the results and to present most demanding requirements. Well, idea if you have sorry, someone is speaking. Please, can you mute your mic? All right, thanks. Idea is to combine several tests like merging energy, electricity, mechanical test, and fire, and to reach final results. When we have developed in this project, it's a ratio results, a combination of results leading to 3 different ratio results. If the ratio is equal to 1, we haven't any modifications in terms of fire results on BIPV elements. If ratio is upper to 1, we are able to reach upper results, and of course we are BIPV elements pass the test. And unfortunately, if the ratio is lower than 1, that proves that the element is not convenient for building applications, and we have to make some improvement to reduce the risk of fire resistance of fire capabilities of the elements. Well, as the final pictures, here is the final diagrams of what we want to realize in the BIPVBOOST project. And when we have a focus on the fire test procedures, we have conducted a combined test of fire tests under electrical load in order to investigate if the presence of electricity load during the fire test could bring better or lower results. And is expressed with a ratio RFR in order to know if we are able to pass or to fail the test during these new test procedures. In order to conduct this kind of tests, we have developed a specific setup with an electrical DC load applied on the PV mockup during the fire test. It's composed of these PV DC generators in reverse mode connections with electric capability, just to be sure that we are able to provide or to push enough energy on PV systems, and to be most demanding in terms of STC conditions, and to reach more than 1000 voltage, and to stick to the max current produced by PV elements. This configuration is adaptable to any kinds of PV systems with IIGS, SE systems, mono or polycrystallines, up to 10 kilowatt peaks. Here is a small pictures of the software allowing us to control the DC load during the fire test with a small period of stabilizations. And you have a representation of the test duration during the B-roof test. Then the picture of what we have conducted. Here is a SBI test on Onyx and PIDS elements. And during the fire test, we have applied an electrical load in order to be as close as possible of real test conditions. Here you have a picture, some pictures, sorry, before, during, and after the fire test. You could have some results on bus bar failures, junction box failures, but we observed no fire penetrations and no destruction of electrical connections. Here is some results on the most representative results are RR, THR, FIGRA, and SIMGRA. It's the main result of SBI tests. As you can see, we have a good fire, not good results, but we have fire propagation, but not a large acceleration of fire or energy generation during the test. And as a final results, what we observed, it's this kind of configurations is able to pass the test and to reach BS1D0 classification, sorry. In indoor tests with exactly the same standard test conditions, and during the new test procedure, when we applied a maximum power load, we do not change the final results. That means that this configurations is not sensitive to an electrical load. As you can see on this small video, it's test progress on SBI test for crystalline elements. When final results, it's that we have passed the test, we have validated the methodology, and we observed no discontinuities and no electrical arcs during the fire test. We conducted exactly the same test procedures on the IGS thin films elements in flexible layers. And unfortunately, we haven't reached exactly the same results because with the presence of very large burning mass in the systems, we reach I'm sorry, I missed something. Oh, okay. Here is the test under progress, and what we observed on the curves, it's after the ignitions of the test procedures, we reach a large acceleration of energy emitted during the test due to uncontrolled fire procedures, and we have stopped the test just to be sure that we do not damage the installations. And what we observed, I'm sorry, I will change it, but unfortunately, with this kind of configurations, we failed to pass the test. And we have its FlySum final classification as ES2D2. And for French regulations, it's not allowed to have this kind of elements for building applications. Well, we have passed the test, but unfortunately, it's not really convenient to use this kind of configuration for building applications. This procedure for roof element. In this configuration, it's exactly the same CIGS elements, but glued directly on aluminium sheet for roofing elements. And we applied exactly the same electric setup. And what we observed, it's pretty good results in this kind of tests. As you can see on this video, in slow motion, we have applied burning elements directly on the roof parts, and we observed no fire propagations to the upper part of the mock-up, sorry, and a self-extinguish procedures or behavior, even if we provide a lot of wind speed and a lot of irradiant energy thanks to heater systems, as you can see on the top of the pictures. Even if we use the IGS element with a lot of polymeric elements, what we observed in this kind of configurations, it's no degradation of the final ratio. And in this kind of configuration, we reach exactly the same fire classification, the same fire results as BROOF T3 than an element without an electrical load, and we have passed the test. Here are some pictures of final results and observations. On the red circles are the places of firebrands locations. And sorry, I flipped the pictures, but is a small zooms on what we observed on PV elements. And we haven't propagation on the upper part.
Hello. I think our presenter had a connection problem. I don't know if Jose Maria, you can see him, or it's just me.
No, I think we lost. I think we lost Simon.
Yeah, I think we have lost Simon. So I don't know what you will do. We can continue with Daniel Valencia, or we can wait for him. I don't know what you suggest.
Let's wait 1 minute and see if he manages to come back.
Okay. Okay.
I guess he's about to finish.
Yes.
Otherwise, we move on to Daniel.
Yeah. So for now, I would like to remind you that the next presentation will be about energy economy, and it will be given by Daniel Valencia from Tecnalia. So now we are waiting a little bit for Simon, that he got disconnected. So yeah, we're gonna wait for him a little bit. If not, we continue with Daniel if everything is fine.
Okay.
I don't think see him coming back.
Yeah, okay, let's move to Daniel then.
Yes, if it's fine for everybody. Yeah, we would like to welcome Daniel Valencia from Tecnalia. And he will speak about energy economy, as I mentioned before. Thank you, Daniel, for being here.
Yeah, thanks to you for prepare everything. And well, it's a pity not to hear Simon because it was quite funny to see and quite interesting to see the things burning. But well, let's continue with the energy economy topic. I will talk about mainly about the photovoltaic IGU. IGU is the isolated glass units. So this means double glazing with a gas cavity in the middle in order to reduce the thermal transmittance. So, and in this case, we have analyzed what happens when we introduce the photovoltaic elements in this type of glazing. And in particular, we will talk about the operating temperature of these systems, the dynamic U and the G values. So this is a common IGU unit. Sorry, I'm going to take the laser. Yeah, so we have here the gas cavity between two glass layers, normally 4 millimeters glass or so. Then the outdoor conditions, the indoor conditions. So something similar that to the glazing that we see here in the bottom. And what happens when we introduce what we transform this glazing system into photovoltaic glazing system. So we introduce here the solar cells and then an additional glass layer, normally low iron glass. So this is a high transmittance glass. And so this glass system is similar to the glazing that we see at the top of the picture. And then we will have the solar radiation that will be partially absorbed by the solar cells. So this part will be heated up due to the radiation that is absorbed. A part of this absorbed radiation will be transformed into electricity, so will not be as heat in the system. So he will be transformed into electricity. And then we may wonder what happens with the different parameters that are used for the calculation of the U and the G values. So like, for instance, the delta T, the temperature difference between these two glass surfaces, the average gas temperature that we have here in the cavity, also the maximum gas temperatures that are linked with the cavity, the maximum cavity pressure that we can have here. Also, we may wonder what happens with the external surface resistance, which is linked with the convection and radiation effects, and the same for the internal one. And also what happens with the heat direction, because even as this part is heated up due to the radiation absorption, even in winter, we may have the heat flux from the outer to the inner side. So because of these additional or new effects, we have reviewed all these standards, most of them related with the calculation of the U value, some others with the G value, some others with the general energy performance of buildings. And with this new phenomena in mind, we have select different points where the introduction of the photovoltaic may impact. And well, just a quick overview. So like, for instance, the introduction of the photovoltaic elements may impact of, as I said, in the gas temperature, in the delta T, the U, the G, the thermal dependence of the efficiency. Also, we may wonder, I haven't mentioned in the previous example, but we may wonder what happens with the junction box and how it impacts on the U and G value. Also, the distribution of the solar cells in the glazing, the light transmittance of the different solar cell technologies, but some of them have important transmittance in the near infrared. Also, the value of the heat transfer coefficients and the impact of higher cavity pressure. Well, this presentation is focused on these points that we have analyzed by means of a PV glazing thermal model. Also, some of them we have analyzed using finite element method simulations. And some others have been also analyzed in the context of the BIPVBOOST project and will be published soon, probably in the following months. So let me explain a little bit about this PV glazing thermal model that we have used, just key ideas to let you know the assumptions that we have made. We have a 16 millimeters cavity with argon. The emissivity in this outer face is the normal one of the glass. The emissivity here is the common for the low wind coatings. Then we consider the direct and the diffuse radiation from the meteorological data. Also, we consider the angular radiation losses that we will have depending on the sun position compared to the glazing position. We take the external temperature from meteorological data as well. We consider the internal temperature 22 degrees. We take the external and the internal surfaces resistances from the standards. And also we assume that we have a PV efficiency of 20%, which is common for crystalline silicon solar cells. Then we will have this thermal circuit. The equations that we have considered have been taken from these standards and are already known. So we have analyzed these systems for these three locations. So we have taken this meteorological data from these three locations, Madrid, Brussels, and Stockholm. Then we have also analyzed different PV occupancy ratios from 0% that would be a common glass without any PV element, and a fully covered photovoltaic glass. And also for different orientations of facade, a facade facing east, south, west, and north, and a skylight with two different inclinations. So what we have are results more like this. So for the three locations, Madrid, Brussels, Stockholm, the different facade cases, the different skylight cases, the different PV ratios for each case. And in this example, we are showing the parameters related with the gas temperature, so the temperature here in the cavity. And well, I'm not going too much into the details, but just to show you a little bit. Like for instance, the maximum gas temperature that we have seen is for the skylights in Madrid facing south. And then we have other indicators like the average gas temperature of the yearly average of the gas temperature, and the average during the winter, for example. So as one of the main results that we have seen is that the yearly average of this gas, comparing the common IGU and the photovoltaic IGU, are more or less the same, nearly the same. The photovoltaic have only 1 degree higher temperature in average. This is the yearly average. And it's curious that is significantly higher than the gas temperature described as default value in this standard, which is 10 degrees. We have done the same for the delta T. And what we have seen is that we have the same delta T in both cases, and is significantly lower than the delta T described in these standards. In order to analyze the maximum temperatures that we could have both in the cavity and also in the PV glass, we have gone for a worst case scenario, and we have described a scenario with an indoor temperature of 29 degrees instead of 22. Eliminating the PV conversion, so we are in open circuit state. This is a skylight in Madrid that we have seen that is one of the worst cases, and a higher external surface resistance, which means lower convection of external surfaces. And I will stop a little bit here because this parameter depends, as I said, depends on the convection and the radiation. And the convection strongly depends on the wind velocity adjacent to the surface, which is normally unknown. So we have a high variation from an unknown parameter that we have there. And just for contextualize, the default value of external surface resistance normally is 0.04, and this is almost or quite near from the minimum value that we have calculated for Madrid, because this parameter, the external surface resistance, can be up to 0.09. So what we have done is analyze the temperature depending on the values of this external surface resistance that, as I said, depends on the wind velocity near the glazing, and for different PV ratios. And what we have seen is that the gas cavity temperature, so the temperature here, can go up to 80 or even 83 degrees in some cases during some short periods. And the temperature of this PV glazing can go up 100 or even in very, very bad conditions up to 120. And as I said, we can see here that this temperature strongly depends on this parameter. Like, for instance, it is not the case for the normal glazing without PV, but when we introduce PV, so like the 80 or 100% of the area covered with PV, it strongly depends on the wind velocity. So just as a summary of this point, we have that the cavity temperature, the maximum temperature of this cavity that can be reached is much higher in the case of photovoltaic, that can be between about 70-80 degrees instead of 45 degrees. And regarding the temperature of this first glass layer, in the case of normal glass, this can reach 45-50 degrees, but in the case of photovoltaic glass, can reach between 90 or even in very, very bad conditions like 120. And well, these are the results for the U value, and very quickly, let's have a look to them. We have seen that the U value is quite similar for every facade case, and also it doesn't matter the location. But in the case of a skylight, we may have small variations. And a summary of this point, we see that the average U value among all the cases calculated for the PV glass is about 1.06, which is quite similar to the normal glass, and also quite similar to the value calculated with the standards. However, for the skylight case, we see that the U value could be slightly lower when we introduce the PV, the PV layers. And so this is, we will have better U value introducing the PV. And this is mainly because, as I explained before, this outer part sometimes, even during the winter, is hotter, so the heat flux direction change. And in some cases, the heat flux, even in winter, goes from outside to the inner side, which is quite low in this horizontal configuration. So as conclusions, we have that the average temperature of the cavity and delta T is similar for vertical PV and no PV cases. We have that the temperature of the cavity is significantly higher than the one proposed in the standards. However, the delta T is lower, so one deviation offset the other. And that's why the final U value calculated with the standards and the average dynamic U value are quite similar. For the case of skylights, we have seen that introducing the photovoltaics, we can slightly reduce the U value. And also we have seen that the external surface resistance strongly impact the temperature behavior of PV glazing, much more than the impact to the normal glazing. And the gas cavity temperature can go up to 75-80 degrees in most conditions. So we have to consider this regarding about the cavity of this glazing. And finally, as future work, even though we have use for this model already known equations and already validated equations, but we would like also to validate our model with this experimental campaign where we have introduced several sensors in a PV glazing. Also, we plan to publish an article with the details of all these studies. We plan also to use these results for the new standards and the prenormative research within the International Energy Agency Task 15 group. Another future work that could be done is the investigation and comparison with other PV glazing thermal models, like the one described in 15099. And finally, the modeling and results for triple PV-IGU instead of double, that is the ones that we have shown here. Well, thank you very much for your attention.
Thank you, Daniel, for your presentation. Now we would like to welcome back Simon. He will finish his presentation. Simon, have in mind that we are past the time, so we will ask you to be not so long.
Yeah, I will be as short as possible.
Thank you so much.
Well, let me know if you see my screen correctly.
Yes, we see.
Yeah, I will switch off my camera because we have some issues with our network. Sorry. Yes, just to jump to the final video on B-roof systems. If you remember correctly, what I showed you just before, it's a Brendan test for B-roof test, T3 B-roof test. And what we observed is a self-extinguish of fire propagations, and it's very good results for Primerix elements. And we have validated final results of these new test procedures in standard test conditions, but also in the new test procedures developed in the BIPVBOOST project. Sorry. Well, what we have observed also, it's for B-roof test, we have not observed, any significant deviations in terms of final results, even if we are applying an electrical load during the fire test. And we passed the test and we have validated this methodology. And in terms of an electrical point of view, we do not observe any discontinuities and any electrical arcs. Are some pictures of results that we could observe on the IGS elements with no fire propagations, no spread fire on the upper elements on the roof IPV systems. And it's quite interesting for French market because according to B-roof T3, it's strongly observed as crucial parameters. And if we haven't a propagation of fire until the upper part of the mockup, we pass the test. Well, in terms of conclusions, what we could conclude is that we have validated the new test procedures on the combination of building test and electrical load. We will have to apply these new test procedures on any kind of BIPV categories on the roof, but also on the facade. And it's quite interesting for labs because they will be able to handle this kind of procedures in the same labs with exactly the same electrical setup. And we are able to take into account any cells components. I mean that we could apply this kind of setup on IGS, but also on silicon cells. It's also a way to save time and cost because all tests are conducted in the same time, at the same place, in the same locations. And it's a strong way to support manufacturers in components definitions in order to fine-tuning elements, materials, and so on. It's also a way to accelerate market access for several BIPV solutions and cell technologies. And it's also a way to ensure proof of confidence, or to provide more confidence for insurers to adopt BIPV in building projects, with no additional risk observed, even in most demanding conditions. And in perspective, what we could talk about, it's a specific electrical load definition is currently in progress, because we have to work on this way with the arc detection by modules, with an identification with high accuracy of weak points on PV installations inside to support improvement and BIPV optimizations. Well, next step will be to integrate other new test procedures in the process and accelerated aging effects, because that could play a significant role, to reduce our shorter standard procedures to save more times and to be more interesting for manufacturers, developers, and installers, and to support the definition of specific BIPV standards to boost BIPV markets. Well, it's over. Thank you for your attention.